My name is Mogens Steffensen. I'm professor in insurance mathematics at Department of Mathematical Sciences, and I'm going to talk about insurance math. And this is a discipline within mathematics, an applied discipline where we are discussing, for instance, insurance pricing using advanced mathematics and probability theory and statistics. If you want to apply these techniques for realistic instruments, for realistic contracts, it becomes rather involved also with the notation and everything. So the ambition here is just to show you a little bit about the principles, the things that you have to discuss, things that you have to formalize. And in order to get to the point, I'm just looking at a very, very simplified contract, but yet complicated enough to make a demand for relatively advanced arguments that we draw from probability theory and statistics. So this is an applied mathematical discipline, as I said, and also very market near. So we have discussions with the industry, the insurance industry and the pension industry about advanced mathematical tools for being more and more delicate in the calculations of whatever we want to calculate in this respect. So, I'll return to some of the things that complicates matters a little bit, but in the first couple of slides I'm just going to try to convince you about ideas of pricing insurance contracts for a very simplified contract. So we're looking at a pension contract where we are making an agreement that a policyholder is going to achieve 1 million units of some currency, crowns or euro or whatever you like, if he survives until retirement. So the formalization here goes in the following way. The capital T is his lifetime, which is unknown. It's a so-called stochastic variable, so it's not something where we don't know the outcome yet. We have to experience his lifetime, and then there is an outcome. But at time zero, when we're going to price this contract, we don't know how long he will live. And the contract says that if T exceeds the retirement age N, say 70 years, then he'll receive 1 million. Otherwise, if he dies before, he'll receive nothing. So X here is also a stochastic variable. X is just a 1 or 0 depending on whether he survives age 70. And this amount is then what he will receive. So first, this million will be received by the policyholder not now, but at his 70 years birthday. So the first thing we have to do is to calculate a so-called present value by multiplying with such a factor here, so-called discount factor that we use to compare values of money paid at different time points. So this is paid at time n, but we want to evaluate it at time 0. And therefore we have this discount factor. If you know interest rate theory, you will recognize it. Otherwise, this is where you learned it. And now I'm going to propose a premium for this contract. I'm just going to take the 1 million times the discount factor and then times a survival probability, so the probability that the lifetime exceeds age 70. And now on the next slide, first I'm going to give you an example with numbers here. What are realistic figures here? So we have the 1 million. What is a realistic figure of the discount factor and the survival probability of, say, 30 years, say a person at 40 years buying this contract that will be paid to him when he's 70, could be the price here. 1 million times 0.5 is the discount factor, 0.8 is the survival probability, and that's the price. So he will be charged 400,000 crowns or euro. And on the next slide, we're going to build up the probabilistic argument why this is a reasonable price, why this is a fair price. So here I just repeated the premium that I just mentioned before. And now comes a fraction where in the numerator here, first what you see here is a sum of 1 million times xi. What we consider is a situation where we sell this contract to M policyholders. And xi will then indicate survival of policyholder number I. Right? So this sum here just counts up all the 1 million euros that has to be paid out at time n. So this is the outflow, the outgo at time n. What is the income at time n? Well, the M policyholders, each of them paid a premium like this, the one that was proposed up here. But this was paid at time 0. So now I want to subtract it from a time n value. So I first have to evaluate it at time n, and I do this. What happened is that I put this premium on the bank account, and it accumulates interest rates, right? And then this interest rate on interest rates produces such an accumulation factor there. And now we can divide by m, such that we have the deficit per policyholder. And then we can plug in the premium from up here and rearrange a little bit, and then we get the 1 million times a bracket, where I simply have the proportion between the number of policyholders who received the million and the total number of policyholders. And this is a classical ratio where you compare the favorable outcomes over the possible outcomes. Right? This is the favorable outcomes over the possible outcomes. M policyholders could have survived, but this is the number who did. And this is a ratio that you probably know from throwing a dice or flipping coins in your math classes when you were taught about probabilities. Right? And then you probably also learned that such a ratio between favorable outcomes and possible outcomes, when you repeat the same exercise over and over again, this fraction that tends towards the probability of success. And this is exactly what I exploit here. I subtract the probability of survival, this is the probability of success, and then there will be, this difference here will tend to zero. Right? So it's exactly the same argument, it's the same law of nature that we use in probability everywhere, here applied to insurance contracts. And this is the argument why this is a reasonable premium, because no matter whether I multiply this thing that tends to zero with 1 million, it still tends to zero. And therefore, so to speak, the business is in balance. There's no deficit, there's no surplus per policyholder as the portfolio grows. Right? This convergence here, this tendency here is when M becomes large. Okay, so now to a sort of sophistication of the contract. The problem with this contract is, for instance, that you will get 1 million paid out. But is 1 million necessarily what you need? No. What you would want is that something that you can buy some goods for, right? And you don't know what kind of goods you can buy for 1 million euro in 30 years from now, because you know that time deteriorates value of money. And this is what we want to account for in a sophistication of the contract, where we're going to say that the policyholder will receive not 1 million euro, but a number of stocks. And then he hopes that the stock price sort of develops similarly in some sense to the prices of the goods that he wants to buy as a retiree. Right? That's the idea, and that's the formalization here. So he'll get a payment of 50 stock prices. Think of Maersk stocks SN. So this is the Maersk price after N years at his 70 years birthday, and then again dependent on whether he survived that far. Otherwise he should receive nothing, because he doesn't have demand for buying goods if he died already. Now, what is now the fair premium? And here's a proposal. I just take the 50 stock prices of today and multiply with the survival probability. And now the question is whether we can create an argument similar to before that sort of explains why this is a reasonable price. The ratio here looks more or less the same. So here we have in the numerator, in the first place here, we have the total outgoes from the insurance company. So for every survivor, we have to pay out 50 stock prices, whatever that is, at time n. On the income side, we have M persons, they paid the premium. Now before, they took this on a bank account and earn interest rate on it. Now we're going to be a little bit more strategic here. Since we are having a payout in terms of stocks, we could choose to actually buy stocks for the premium that is paid at time zero. And this ratio here is the number of stocks that we can afford. Right? This is the numerator is the amount paid. This is the stock price at time zero. So this is the number of stocks we can afford. And then we'll multiply by n to check what is the inflow if we sell all these stocks at time n. And this becomes the income. So the outgo minus inflow per policyholder, and then we again rearrange a little bit, take the 50 SN outside, and then we have the same bracket as before, with the same arguments the law of nature of probabilities makes sure that this tends to zero, because this is just the favorable outcomes over possible outcomes minus the probability of success. And then one has to be a little bit careful on the technical side. Is this now still true? Although we multiply something which tends to zero, but we multiply it with a stochastic variable that can be arbitrarily large. Is it then true still that the product tends to zero in a way such that this is a decent argument for this premium? And it is true. I can promise you it is true that you can argue that this tendency is meaningful with respect to this settlement of the premium. So this is classical insurance mathematics, but then we added this argument here, and this is the important takeaway from this slide, that the value of the thing is closely connected to the investment strategy, right? The reason why the argument for this price was dependent on a specific investment strategy. And this is really not classical insurance math. This is really what we call financial math, which is the mathematics that deals with pricing of goods and their relation to the investment opportunities that the individuals have. And this is crucial, this connection between pricing and decision making in the investment market. So this was pricing of these stylistic simplified contracts, yet rather sophisticated here with a stock-dependent payout. And now on the last slide, I'll just explain you why you're not fully qualified insurance mathematicians yet. There are a couple of other things. Well, first we take the numerical example here. 10,000 is actually the stock value of the Maersk stock today, and 50 of them costs 500,000 times the survival probability gives the 400,000. So actually the price of this contract would be the same as the price of getting 1 million, and then it's up to you to decide whether you want a fixed amount or whether you want something that you think is protecting your buying power. So as I said, finally, what kind of sophistication did we not take into account here? Well, for instance, these contracts typically hold so-called options that the policyholder can, for instance, come at an intermediate time point before time n and ask for a specific amount, which is stated in the contract that if he comes at age 60, you can get this amount. Right? So there's an additional choice of him to make as the contract evolves. And this has to be counted into the premium, and this is rather sophisticated. Another thing is that maybe he's a little bit afraid that the stock price will go down, and he will not be able to buy the newspapers and the milk that he thought he would, and then he buys a protection towards a crash on the Maersk stock, and say that he wants the 50 Maersk stocks or 1 million. Whatever is the largest, right? The maximum of the two. So if the stock goes down, he should get the 1 million. If the stock goes down such that 50 stock price is below 1 million, then he wants the 1 million. So actually, this again has to be priced in. Now this contract costed 400,000. This contract costed 400,000. If he should receive the maximum of the two, what would be the natural price? It's a very, very sophisticated problem, but the point is that the underlying ideas are similar to what we have used here. And then finally, classical insurance mathematics takes into account that these contracts are typically also much more delicate in the structure. Typically, you have so-called disability annuities that would pay out a benefit as long as you are sick and cannot participate in the labor market. Typically, they would have some death sum paid out to your dependents if you die. And there will be a so-called level premium. So you cannot typically afford the 400,000 up front, right? So you want to pay that as a premium per month, for instance, as a percentage of your salary or something, right? So these such pension schemes, pension contracts contains all different kinds of these aspects, and then the point is now then to level the payment coefficients of all these features of the contract such that it's fair, and that has to be taken into account. So this is classical insurance math. These are actually sophisticated enough for me to say that these are topical discussions in the market about modern regimes for accounting and solvency, so accounting standards when you do the accounting as an insurance company. Taking these things into account are, for instance, things that we could discuss with the insurance market to do that on a sufficiently delicate way to meet the demand of the financial market or the policyholders or the supervisory authorities or whomever demands something. So finally, these are all the sophistications, but the ambition here was actually just to spend a few minutes and a few patterns of thinking to realize what are the fundamentals in pricing. We talked about the favorable outcomes over possible outcomes, and we discussed this idea that prices somehow are connected to what kind of investment possibilities you have. These are the core ingredients. Also, if you add these things, these are the core ingredients, and hopefully you got the feeling about how the story goes.